So I'll conclude this lecture by giving you a future outlook, a flavor of the hot research topics nowadays, and what to expect in the next 10 years or so from the magnetism research community. Before I go on, I would like to describe one of the most modern tools of condensed matter physics today, which is the scanning tunneling microscope. This is basically, it functions in the same way as an atomic force microscope, and you have a sample surface here and a tip which is atomically sharp. By applying a bias voltage, one can cause electrons from the sample to tunnel to the tip and vice versa, and through the insulating air barrier. And this tunneling current is very sensitive to the electron density of, or the local density of states of electrons at the surface of the sample, and in this manner one can map a sample with atomic resolution. So this is what one can do with an STM. This is a 2-atom thick lead film. The scale here is 10 nanometers, and each of these is an individual lead atom. This is the same done on a silicon surface. The power of STM is not just mapping, it's also manipulation. One can actually use a voltage, a bias voltage, pick up an atom from one side and put it at another, and that is a very powerful aspect of this instrument. And this was demonstrated as early as 1990 by Eigler and Schweitzer at IBM, where they decorated a nickel 11010 surface by writing IBM on it with individual atoms using scanning tunneling microscopy. This is another work by the same group which was published in Nature 3 years later, and here they have, this is known as a quantum corral. And a corral is something which was used in the American Wild West. It's an enclosure where horses and cattle were kept. So this is basically that kind of an enclosure that is called a corral. And each of these spikes is an individual iron atom. And what they showed was that by making the structure, they can actually see the electron waves. The ripples here are the electron waves inside this corral, which are generated on the copper 111 surface. So this is an extremely powerful tool for modern day research. We're talking about magnetism, so of course we are not just interested in scanning tunneling microscopy, we are interested in spin polarized scanning tunneling microscopy. So this is basically just applying the concepts of spin polarized transport, which we looked at earlier, to STM. So here we have that if the tip and the sample are magnetized in the same direction, there will be a large current, and if the tip and the sample are magnetized in opposite direction, then there is a small current. If you look at the diagram of the density of states here, because there are empty states into which the tip current can, or the tip electrons can tunnel into. So in this manner one can map out the magnetic states of the sample, not just where the atoms are lying, but whether they're magnetized in a certain direction. And you can even magnetize individual atoms as you want them to be. This, for example, is some work from the group of Professor Wiesendanger at the University of Hamburg. This is very recent work, and here they show that they can make iron atoms antiferromagnetic, which is very, very interesting, because iron, we know, is a ferromagnet. Everybody knows that iron is a ferromagnet. But if they place iron atoms at specific distances from each other, for example, if this is, let's say this is a cobalt island which is magnetized in a certain direction, then if I place an iron atom next to it at a certain distance, then the iron atom will necessarily be magnetized opposite to it. So the yellow here means a downward magnetization, the blue means an upward magnetization. And this coupling is controlled through the substrate. This is an effect known as the RKKY coupling, where the direction of magnetization depends upon the distance between two magnetic objects. So if I can control this distance very precisely at an atomic level, then I can control the magnetization. And this has applications in spintronic logic devices. For example, this is an OR gate. Here I have an input alpha, here I have an input beta. So if this is down, and if I use my STM tip to place the atoms exactly where I want them to be, then I can have spin up, spin down, spin up, spin down, spin up, and spin down. And so if either of these is in a down state, I'll get a down state here. So I can build a spintronic OR gate using this, using STM. And similarly, they have demonstrated other kinds of logic devices too. Another very interesting thing that people are looking into are non-collinear spin structures, where the spin is forms different kinds of helical patterns, circular patterns, and the idea is, can we utilize these for quantum computation and quantum information processing. The STM also allows you to control spin dynamics and manipulate individual spins. So it actually allows you to write the spin on this atom by the STM tip. So you can use the STM tip to overcome the anisotropy energy barrier and flip the direction of an individual atomic spin. So these are just some of the very, very interesting things that are being done in magnetism at the atomic scale. Some things which you might want to look up, which are also very interesting, are molecular magnets, topological insulators. These are fascinating objects in condensed matter, and they're fascinating because the bulk is insulating and the surface is conducting. And in fact, it can be made to conduct in a spin polarized manner. So you have different spin channels that can be made to conduct in topological insulators. And graphene, of course, is a fascinating material, and because it has a very unique band structure which consists of 2 Dirac cones. And the idea is, again, how graphene can be used as a magnetic material, or how the electronic density of states of graphene can be used in conjunction with magnetic materials. So I would like to conclude by stating that magnetism is one of the oldest known phenomena to man, but it is still one of the least well understood problems in condensed matter physics. So especially with the power of the STM and other devices which can study magnetism at the nanoscale, and not only study but also manipulate magnetism, not just at the nano but at the atomic scale. There's a huge vista of research areas and interesting problems which is open to, and which is there to be studied and to be investigated. Thank you for your attention.